Dear students, after studying this module, you shall be able to identify various types of reactive intermediates, know the difference between transition state and an intermediate, evaluate the stability of various transition states, analyze any type of reaction coordinate diagram, and learn about the very important Hammond postulate, reactive intermediates. Now, what is an intermediate? An intermediate is a species formed in a stepwise reaction which represents a free energy minimum. For example, look at the figure which shows the formation of an intermediate, let us say a carbocation here, during hydrolysis of tertiary butyl bromide. Now, as you can see, it represents a minimum. Now, the various types of reactive intermediates which are known are carbocations, carbanions, free radicals, carbenes and nitrines. Carbocations, also known as carbonium ions, these are species in which a carbon atom bears a positive charge, is trivalent, sp2 hybridized and has a planar structure. Now, this is clearly seen in figure, as you can see here, the hybridization state as well as the structure of a carbocation. The more stable carbocations have been prepared in solution and in some cases even as solid salts. Now, among simple alkyl carbocation students, the order of stability is tertiary greater than secondary greater than primary. Now, there are many known examples of rearrangements of primary or secondary carbocations converting into tertiary ones because they are more stable, both in solution phase and in gas phase. Now, the most stable of the simple alkyl cations is obviously the tertiary butyl cation. Now, let us move our focus to carbanions. Carbanion has a trivalent carbon that bears a negative charge, is sp3 hybridized, tetrahedral, has one lone pair and is electron rich. By definition, every carbanion possesses an unshared pair of electrons and is formally a base. The stability of the carbanion is directly related to the strength of its conjugate acid. Now, the weaker is the conjugate acid, the greater is the strength of the base in the form of carbanion, and the lower is the stability of that carbanion. Now, in this figure you can clearly see the hybridization of carbanion and its structure. Now, let us come to third type of intermediates, free radicals. Now, free radicals are sp2 hybridized, planar and neutral species with an odd electron in a perpendicular p orbital. As with carbocations and carbanions, simple alkyl radicals are very reactive and are usually transient species. Now, in this figure you can see whatever I said, the structure and hybridization of a free radical. Now, students, let us consider very important type of intermediates called carbenes. These are uncharged reactive intermediates with a divalent carbon atom. Carbenes are highly reactive species and practically all have lifetimes considerably less than 1 second. The parent species methylene or CH2, although derivatives are more often named by carbene nomenclature. Although the parent species is methylene, that is CH2, the two non-bonded electrons of a carbene can either be paired or unpaired. Now, if the two non-bonding electrons are paired, then the species is spectrally called a singlet, while the two unpaired electrons, they appear as a triplet. Now, you can clearly see this in this figure, the hybridization and the structure of carbenes. Now, another important transient species is a nitrine. These are uncharged electron deficient species containing a nitrogen atom with 6 electrons in its valence shell. Now, these are analogous to carbenes with respect to electronic structure, that means they are isoelectronic with carbenes, methods of formation, detection and modes of reaction. Now, nitrines are too reactive for isolation under ordinary conditions. You can see the structure of nitrine in this figure. Now, let us come to transition states. What is a transition state? A transition state is a configuration of maximum potential energy which is reacting molecules must pass through. Now, the transition state cannot be isolated, it is unstable and it is only a transient arrangement of atoms on the pathway from one intermediate to another. Transition state has high energy since old bonds start breaking to form new bonds. The transition state is represented by a double dagger symbol as it is shown here in this figure, and the free energy of a transition state is represented by delta G with a double dagger symbol. The energy difference between the reactants and the transition state is called the activation energy and is represented by EA. A catalyst lowers this activation energy to reach the transition state. There may be more than one transition states for a particular reaction. Now, that is generally in multi-step reactions. This you can see in the figure. Now, in this figure, the local minima represents reactive intermediates and also the local maxima are transition states. The highest transition state determines the overall reaction rate, and the step with the highest energy, that is the step with the highest energy transition state, is also the rate determining step. Now, you can clearly see all this in this figure. This is the reaction coordinate diagram for a multi-step reaction showing the transition state and the intermediate. Now, let us consider some examples of transition states. First is the addition of HCl to ethene. Now, a CC bond is double in the alkene, that is in the reactant structure, while addition of HCl to alkene, the transition state must be intermediate between a single and a double bond. Now, this is represented as a full line for the sigma bond and a dashed line for the partial pi bond. Now, the new CH bond made and the HCl bond in the transition state is between no bond and a single bond. It is represented by a partial bond, that is a dashed line or a dotted line. Now, you can clearly see this in this figure how a transition state involves a partial bond which is represented by a dashed line. Now, let us consider the second example which involves the abstraction of hydrogen atoms from an alkane by bromine. Now, the abstraction of hydrogen atoms from an alkane by bromine atoms has a transition state with a radical character. Now, you can see this in this figure. As the bromine abstracts the hydrogen from this alkane, a partial alkyl radical character is introduced in the transition state. The third example involves hydroboration. Although the transition state for addition of borane to an alkene has reactant and both product character, the transition state has additional characters not present in either the reactant or the product. Now, as a consequence, there is a carbocation character at the carbon to which the hydrogen becomes attached. Now, this is a new type of transition state which has some characters which are present not only in reactants and products, but also apart from them. Now, you can see this in this figure, it is clearly shown. Now, the fourth nice example, a very important example, is the E2 elimination reaction. Now, E2 elimination reactions have predominant alkene, that is product like character in the transition state. There is also a significant carbanion character at the beta carbon in the transition state. Moreover, in some cases it becomes the dominant character, and certain elimination reactions prefer to yield the thermodynamically less stable alkene. Now, you can clearly see this in this figure which is involved, in which after the E2 mechanism the alkene is yielded. Now, The fifth example is a reaction of an unsymmetrical alkene with unsymmetrical reagent. The reaction of isobutene with hydrogen chloride could generate either or both of the two products, that is tertiary butyl chloride or isobutyl chloride. Now, these products formed are determined by the outcome of a competition between two distinct transition states. Now, one of the transition states, if you see, has a tertiary carbocation character and the other transition state has a primary carbocation character. Now, as I have already told you when we were discussing the carbocations, the tertiary carbocation character is more favorable than the primary carbocation character because a tertiary carbocation is more stable than a primary one. Thus, the transition state for the formation of tertiary butyl chloride is preferred over the primary. Thus, one of the products, that is the tertiary butyl chloride, is obtained with a higher level of selectivity. Now, it is easily seen, it is clearly shown in the figure, the reaction of isobutene with HCl and the preference of the tertiary butyl chloride. Now, let us come to the next example, the SN2 reaction between hydroxide and chloromethane. The SN2 reaction involves a collision between two molecules and the reaction proceeds via a transition state as shown. Now, this is another type of transition state in the SN2. Now, you can see we have noted down almost all the examples in which various types of transition states are involved. Now, students, after having considered the reactive intermediates and the transition states, let us come to potential energy diagrams. Potential energy diagrams illustrate the potential energy of the reactants and products for a chemical reaction and how this energy changes during a particular course of reaction. The potential energy measures the energy stored within the bonds and phases of the reactants and products. This potential energy is a part of the internal energy. Now, in chemical reactions, the internal energy represents the total energy of the system and is often called as enthalpy. Now, during a chemical reaction, students, the enthalpy or heat content of the reactants changes into the enthalpy or the heat content of the products into which they are converted. Now, you can see this in the potential energy diagram of a reaction as we have shown. Now, what is a reaction coordinate? The reaction coordinate represents the extent to which the coordinates such as bond lengths, angles and dihedral angles of the reactants get converted to those of the products during the progress of a reaction. Now, the reaction coordinate, that is the x axis in an energy diagram or the potential energy diagram as we discussed, is a parameter used to describe the progress of the reaction. This axis could be time, a structural parameter or bond dissociation. The reaction energy profiles help to explain the concepts of activation energy and transition states. The vertical axis is the total potential energy and the horizontal axis is the reaction coordinate, which symbolizes the progress of a particular reaction with reactants on the left hand side and the products on the right hand side. Now, delta H naught is representing the difference between the energy of the reactants and the products. Now, in the figure for the reaction potential diagram, you can see we have the diagrams for irreversible exothermic and endothermic reactions, and this shows a large value of delta H, while in the next figure for a reaction we can see the potential energy diagrams for reversible exothermic and endothermic reactions showing a small value of delta H. Now, you can appreciate this more by looking at this diagram or the figure in which you can see large delta H and small delta H difference. Now, let us come to a very important concept in the potential energy diagrams as we study here is the Hammond postulate. Now, the relationship of a transition state structure to the structure of reactants, intermediates or products is postulated by Hammond in his statement known as the Hammond postulate. Now, the statement says, quote, if two states as for example a transition state and an unstable intermediate occur consecutively during a reaction process and have nearly the same energy content, their interconversion will involve only a small reorganization of the molecular structure, unquote. In other words, the transition state is more similar in structure to the species to which it is more similar in energy. Because the rates of chemical reactions are controlled by delta G with a double dagger symbol, information about the structure of transition state is very crucial to the understanding of various reaction mechanisms. On the contrary, students, transition states have only transitory existence, that means their lifetimes are very small. Thus, it is not possible to make experimental measurements that provide direct information about their structure. Now, in case of an exergonic reaction, the transition state is more similar in energy to the reactant than to the product. Therefore, the structure of the transition state will more closely resemble the structure of a reactant than that of the product. Now, considering an endergonic reaction, the transition state is more similar in energy to the product, so the structure of the transition state will also more closely resemble the structure of the product. Now, only when the reactant and the product have identical energies would we expect the structure of the transition state also to be exactly halfway between the structures of reactant as well as the product. Now, sometimes the terms early or late transition states are also used. An early transition state is reactant like, whereas on the other hand a late transition state is a product like. Now, you can clearly see this in the figure that we are showing you. Now, in an endothermic reaction, the transition state is closer to the products in energy as well as in the structure. However, as discussed before also, in an exothermic reaction, the transition state is closer to the reactants in energy and the structure. Now, you can clearly see this in this figure. Now, examples of reactions involving major transition states. First, we would like to take up with you students electrophilic aromatic substitution as an example of reactions involving the transition states. Now, in electrophilic aromatic substitution, the transition state is discussed in terms of a reaction intermediate. Examples are bromination, chlorination, nitration or sulfonation of benzene, methoxybenzene, nitrobenzene, etc. Now, you can clearly see this reaction is depicted here. All these reactions I have told you, the chlorination, bromination, nitration, sulfonation of methoxybenzene as well as benzene or nitrobenzene and their respective transition states. Second example we will take students is the formation of tertiary butyl cation. The tertiary butyl cation is formed faster than the isobutyl cation when 2-methylpropene reacts with hydrochloric acid, that is HCl, because the formation of a carbocation is an endergonic reaction and the structure of the transition state will resemble the structure of the carbocation product. This means that the transition state will have a significant amount of positive charge on the carbon because it represents the carbocation structure more. Now, the tertiary butyl cation, that is a tertiary carbocation, is more stable than the isobutyl cation, which is a primary carbocation. I will reinstate here students that I have already discussed in the case of carbocations, the tertiary is more stable than secondary than primary. Now you can see the formation of tertiary carbocation here in favor of the isobutyl. The factors that stabilize the positively charged carbocation product stabilize the partially positively charged transition state also. Therefore, the transition state leading to the tertiary butyl cation is more stable than the transition state leading to the isobutyl cation. Now, because of the positive charge in the transition state and the amount of positive charge present is not as great as the amount of positive charge on the carbocation product, the difference in the stabilities of the two transition states is not as great as the difference in the stabilities of the two carbocation products. Now you can easily see in the potential diagram for the formation of tertiary butyl cation. Now coming on to electrophilic addition reaction for an alkyne and the transition state thus involved in it. Now I would like to ask a question here. Why is the transition state for the first step of an electrophilic addition reaction for an alkyne less stable than that for an alkene? Now the Hammond principle predictably has an answer to it. The Hammond postulate predicts that the structure of the transition state will resemble the structure of the intermediate. The intermediate formed when a proton adds to an alkyne is a vinylic proton. Now in the second step of the same reaction, the positively charged carbocation intermediates rapidly with the negatively charged chloride ion. Thus, alkynes like alkenes undergo electrophilic addition reactions. The same electrophilic reagents that add to alkenes also add to alkynes, and that again like alkenes electrophilic addition to a terminal alkyne is regioselective. Now when an electrophile adds to terminal alkyne, it adds to the sp carbon that is bonded to the hydrogen. The addition reactions of alkynes however have a feature that alkenes do not have. Because the product of the addition of an electrophilic reagent to an alkyne is an alkene, a second electrophilic addition reaction can occur. Now an alkyne is less reactive than an alkene. This might at first seem surprising because alkyne is less stable than an alkene. However, the reactivity depends on delta G, which in turn depends on the stability of the reactant and the stability of the transition state involved in the reaction. For an alkyne to be both less stable and less reactive than an alkene, two conditions must hold. First, the transition state for the first step, that is the rate limiting step of an electrophilic addition reaction for an alkene must be less stable than the transition state for the first step of an electrophilic addition for an alkene. And the difference in stabilities of the transition states must be greater than the difference in stabilities of the reactants, so that delta G for alkyne is greater than delta G for an alkene. Now let us consider the hydrogen abstraction for bromine is endothermic but exothermic for chlorine as a case. The hydrogen abstraction for bromine is endothermic as the transition state is close in energy to products, but hydrogen abstraction for chlorine is exothermic as the transition state is more closer to the reactants. Now hydrogen abstraction for chlorination is exothermic because the transition state resembles the alkane and a chlorine atom. There is little radical character on the carbon in the transition state. Thus, regioselectivity is only slightly influenced by radical stability. However, considering bromination of alkanes, the abstraction of hydrogen is an endothermic reaction an endothermic step, and a transition state shows a resemblance with an alkyl radical and HBr. Therefore, carbon atom in transition state has a significant radical character. Now, comparison to chlorination, the activation energy of bromination is much more, so reaction becomes more selective. Now, this is easily seen, the comparison between chlorination and bromination in this figure. The transition states forming for the primary and secondary radicals for the endothermic bromination have a larger energy difference of 9 kilojoules than those forming for the exothermic chlorination, that is 4 kilojoules. However, the energy difference of the primary and secondary products formed in chlorination and bromination is the same, that is amounting up to 13 kilojoules. Now, let us see, students, any change that helps to stabilize the products relative to the reactants shifts the transition states towards the reactants. For example, the transition state for the carbocation intermediate moves towards the reactant as the intermediate species becomes more stabilized, that is in primary, secondary and tertiary. Now, here you can see in this figure the clear depiction of transition states for the carbocation intermediates. Now, some application of Hammond postulates, let us consider them. Easily explains the relationship between the rate of reaction and the stability of the products. It is applicable on electrophilic addition reactions which proceed through the formation of carbocations which are formed by protonation of an alkene and is an endogonic step, that is an endothermic process. It also explains the selectivity of product formation during bromination and chlorination of alkanes. It is also useful in rationalizing the SN1 mechanism of alkyl halides which proceed to the formation of carbocation as an intermediate. Now, there are some limitations of Hammond's postulate. They are: the Hammond's postulate makes a connection between a rate, that is kinetics of a reaction, and equilibrium, that is thermodynamics, which has no theoretical basis. Second one is that the use of Hammond's postulate is based primarily on enthalpy considerations and it neglects the effects that activation entropies can have effect on reaction rates. Third one is that the Bronsted catalysis law, that is an empirical linear free energy relationship law, is valid within carefully chosen groups of acids or bases only. Now, students, let us summarize this module. Now, an intermediate, as we first discussed, is a species formed in a stepwise reaction which represents a free energy minimum. The various types of reactive intermediates are called carbocations, carbanions, free radicals, carbenes and nitrines. The transition state is a configuration of maximum potential energy which the reacting molecules must pass through. The transition state cannot be isolated, it is unstable and it is only a transient arrangement of atoms on the pathway from the reactants to the products or from one intermediate to another. Now, the reaction coordinate represents the extent to which the coordinates such as bond lengths, bond angles and dihedral angles of the reactants get converted to those of products during the progress of a particular reaction. Now, reaction path diagram of a reaction, as I already told you, is a two-dimensional slice of a multi-dimensional energy surface. According to Hammond's postulates, like we have discussed in detail, the transition state is more similar in structure to the species to which it is more similar in energy. In an endothermic reaction, the transition state is closer to the products in energy and in structure, often referred to as the late transition state. In an exothermic reaction, however, students, The transition state is closer to the reactants in energy and structure, also sometimes known as the early transition state.